We have a week off from quizzes now. Your next quiz isn't for 2 weeks from today. I know it's a little late, but so hopefully your holiday, whether you celebrate Passover, Easter, Ramadan, 420 coming up, anything, I hope you get some rest over this next week. And yeah, let's get started. So today we are going to talk about non-steady state flow. So we'll start by reviewing what steady state flow means in a circuit. Remember from last time we have some gradient, which is just a change between a high and a low, whether that's high temperature, low temperature, high pressure, low pressure, voltage, anything. And as a result of that gradient, we get a flow from high to low. So there's also a resistance, right? The higher gradient gives us higher flow. If we have a really hot thing and a really cold thing, there's going to be stronger flow or faster flow than if there was something that was 1 degree higher than the other thing. And then the resistance works in the opposite way. If we have a higher resistance, there is slower flow. And again, this model works for a lot of different systems, anything where there is a high and a low, and it's also steady state, so constant in time. The system is dynamic in that there's just things moving. There's some current flow, whether that's fluid or charge or heat, anything like that, but the actual behavior doesn't change over time. So now we're going to look at what happens if the behavior does change over time and how to describe that with equations as well. So let's see what that actually looks like. And I think the easiest way to see it first is with temperature. So this is an example I think I showed last time where we just have some hot reservoir and some cold reservoir. Think maybe like a lecture hall. This lecture hall is at 90 degrees and the one next door is at 50 degrees. So there's some delta T. There's a temperature difference between two places in space here and there. There's some resistance in between, the wall in between them is going to prevent or slow down heat flow in between the two, but over time it will. We know that, well, I guess from intuition, maybe from 7a, but the temperatures will come to equilibrium. If one's at 50, one's at 90, after we let it come to equilibrium, they will both be the same temperature somewhere in between those two. And the rate at which that happens, like we mentioned before, is related to how big the temperature difference was. So 90 and 50 will happen a lot faster than, let's say, 70 and 60 or something like that. The rate of change, the flow will be higher for the former example. But the thing that we didn't factor into, that we didn't factor into our model before, right? When we just said, this is the high pressure, this is the low pressure. And that's constant. And so there's some flow rate. This is the high voltage, this is the low voltage. This is the high temperature, low temperature, etc. But we know that's not really what happens in real life. Like I just said, things come to equilibrium. As heat flows from the hot to the cold, the hot thing gets colder and the cold thing gets hotter. And so that flow rate that's sensitive to the temperature difference is also going to change. Right? So for heat, we have P, which is power, or that's just the flow of heat. That's our current. And if this delta T that it's related to is shrinking, then the current will also shrink. So over time, this T high, the hot temperature decreases, T low increases, and they come to some sort of equilibrium as the flow rate decreases. So this is what it looks like after we let that happen. They're both at some temperature right in the middle. At that point, our delta T is 0, right? They're at the same temperature, so T high minus T low, T mid minus T mid, whatever, is 0, and there's no more flow. So P, or in general, I, is 0. Okay, so let's take a look at this for a fluid system. Like I mentioned last lecture, you're not going to be, even though you explored heat transfer and osmosis examples in DL, as far as assessments go or the actual math we're going to really be responsible for on quizzes and tests, it's only going to be fluid flow and electrical circuits. So those are the ones that we're going to work the math out for. So let's take a look at this setup we have here. Now this is a system. There's still going to be fluid flow, right? We have two cylinders filled with fluid. One has a higher water level than the other. And so we know kind of intuitively that they will come to equilibrium, right? The high water, the water from the column on the left, the high side, will flow through this middle pipe into the other one, and the water levels will become equal, right? And that makes good sense. And so there's some current in that bottom piece, and we'll just say that that pipe in the bottom has some resistance. So we can use, before we use our Bernoulli's equation, we'll see after some time, same thing with the temperatures becoming like equilibrated or coming to some middle ground temperature that's the same everywhere. Same thing happens for this flow. When the heights are unequal, there's going to be some flow from left to right until they become equal, at which point this is an equilibrium. Everything's happy, right? There's no unequal pressure anywhere, and so the current becomes zero. So our goal today is to model this behavior using our equations. How does I change from this initial value to zero? Like what does that change look like? And how do we describe it mathematically? So we can use our fluid flow equation just like we did before, the caveat being current is no longer constant. So here's our equation, delta P plus change in potential energy density, right? Because I guess we have to be specific about what our delta means here. So I'll say the top of the water level in both columns. So there's clearly a delta H, right? This H is higher than, the H on the left is higher than the H on the right. So there is a delta H, and we have some minus IR term from this resistance in between those two in the circuit. So where do we proceed from here? Well, what's our delta P? What do we know about, I didn't label it here, but from looking at it, what do we know about the pressure of the fluid at the top of both of those columns? Well, yeah, atmospheric. It's exposed to air. So the delta P is actually zero because they have the same pressure. The difference between them comes in with the potential energy density. The one with the higher water level has a higher potential energy density than the one with the lower one, and that's what drives the flow, and we get some current, which gives us a minus IR term. So now we have this clean relationship between the difference in height and the flow rate through the bottom. And that will proceed until, like we said, the current stops and the heights are equal, or mathematically that just means our delta H goes to zero, and the change in height between the two goes to zero. They're the same height. And in this equation, you can see if delta H is zero, then I also has to equal zero. So it makes sense intuitively, and our equation still works to describe this behavior so far. So now let's look at the specifics of how this evolves. We know our endpoints in time. So here's the key that we left steady state, is that there's a difference in time. This is T initial or whatever, T1, and this is our T final after some amount of time. In steady state, these would be the same, but clearly they're not, so we are no longer in steady state. This equation still works, but it has a time dependence. And to be very specific, which pieces have a time dependence, rho, g, and r, those are all constants, right? They depend on the fluid, whatever it is. Depends on the resistance of the pipe, which are just like its physical characteristics, gravity, depends on the planet you're doing this experiment on. But at the end of the day, those things are fixed for this system. But as we saw, delta H and I are the things that change. So now instead of those being constants, they change in time. Yeah? Exactly. Exactly, yeah. You could make a relationship between those two, but the math would be a little uglier. But yeah, we're looking at the difference between the heights of the top of the water in both columns. The reason we can do that is because it is still one fluid system, right? Everything that flows from this side has to flow into this side, right? It's one line of current. There's no junction. There's no loss, anything like that. So we're still good there. So like I said, let's look at what happens in between those two endpoints in time. Which system that I show here will have a larger current? Here we have a system where the water level, the differential, this delta H, is much greater, and this one has a smaller delta H. Intuitively, or at least I would think that this on the left, with the larger delta H, would have a stronger current, right? Because there's a lot of water stacked up on here, a lot of potential energy density. That's going to push harder and force more current through. And that ends up being the case. The one on the left does indeed have a larger current if we take a snapshot in time. So let's describe these both with equations. Again, it's the same one we had before. Delta P is 0 for both because they're all, the endpoints are all at atmospheric pressure. So we just get this rho g delta H equals minus IR. So if delta H is larger, which is the case for the example on the left, then I will also be larger, which is what we just decided intuitively works out. Okay, so now we found that current changes in time and that current is larger when the delta H is larger. Right? So the greater the height differential, the greater the current. So let's switch things up a little bit. This is going to be a very similar type of system, but now instead of starting with two unequal water columns, let's start with equal water levels. So now we're starting with delta H equals 0, but now I'm going to put a pump in this pipe in between the two. So instead of letting gravity bring this to equilibrium and have them settle, we're starting with equal heights and having a pump force this delta H to occur. Right? So if the pump wasn't there, we just have delta H equals 0, I equals 0. But now our equation is going to factor in E pump. So I skipped ahead just to bring the equation up. But we know in time the water level in the left will rise. If the pump is oriented to the left, then it will add energy density. From right to left, we will gain energy density, so water will flow from right to left. And so the current will proceed until it reaches some H, and now the equilibrium state will be when there is some delta H. Right? This isn't just going to rise forever. The pump won't just push water indefinitely up because it has to fight gravity. Right? If we look at our equation now, for the final state, delta P is still 0. Let me just put everything up here. For the final state, delta P is 0 and delta H, I is 0. So now we just have this relationship between delta H, or rho g delta H, and E pump. So let me just take a couple steps back. Originally, we have no delta H. The only things that are working here are the E pump and our minus IR. Right? So there's no height difference, so it's very easy for the pump to pump water from one side to the other. The only thing it's fighting is resistance. But as the water level rises, it not only has to fight the resistance, it also has to fight this change in potential energy density, this delta H. As the water level rises, it becomes more difficult for the pump to push the water. So at a certain point, those two things are going to cancel out. Like we see here, when the current goes to 0, our equation reduces to just rho g delta H. Delta H is no longer 0 because the water level on the right rose, and E pump stays because the pump's still there. So we have no flow, but this is just telling us that the potential energy difference is exactly equal and opposite to the energy density difference introduced from the pump. Right? So in this case, nothing's happening. It's come to equilibrium. The pump is trying to force water this way. Gravity is trying to force water the other way, and they're perfectly balanced. So this is our starting, this is our ending, and we want to describe what happens in between. So the things we've learned, we talked about them with the previous example, but that also apply here, is that the flow rate depends on delta H. Right? Initially, we have some flow rate, and delta H equals 0. And then as we proceed, delta H increases, and our flow rate goes to 0. So there's clearly some relationship between those two things. And we also know that as delta H increases, these two things are saying the similar thing. Delta H increases and I decreases. But that as I decreases, delta H increases more slowly. So this is the key new information on this slide, that the relationship between current and delta H. Current is the flow of water, like volume per unit time, right? It's the flow rate. So if the volume per unit time is decreasing, as we know it does over time, it goes from some value to 0, then the delta H is also going to change more slowly. Because delta H only occurs, the height of the water column only changes because we are pumping water into that cylinder, right? The volume of water in this cylinder tells us the height. I don't do it out on this slide, but we could, if you know the volume of water and you know the dimensions of the cylinder, that tells you the height of the water, right? If I pump more water into the cylinder on the left, the water level will rise. So what that's saying is if I have a high current, my I is large, it will raise quickly because I'm pumping a lot of water per unit time from left to right. And if my current is small, H will rise very slowly because I'm not pumping much water from left to right per unit time. So we don't really need to do any calculus for this class. I'm going to use some terms from it, but it's really just for added conceptual value. You won't have to do any calculus, but really what we're looking at is a rate of change or a derivative. Here I just wrote delta H over delta T. That could be dH dt, like the derivative of height with respect to time. It doesn't matter. Really, it's just a rate of change. How quickly is the height changing? So how much height changes per amount of time? And the relationship we found is that when the height delta H is larger, so when there's a really big height difference, we have a smaller current because the larger height difference makes it more difficult for the pump to function, right? It's fighting. The larger the potential energy difference, the larger the delta H, the more the pump is fighting that. So that reduces the current. And if we have a smaller current, that gives us a smaller rate of change of the height, right? So larger height difference, smaller current, smaller rate of change of the height. So we have this interesting thing where the height is increasing over time, right? The delta H is increasing over time, but the rate at which that's happening is decreasing. So it's increasing, but it's slowing down in how much it's increasing, which is good because we eventually want it to stop, right? We know there's an endpoint when I equals 0, delta H does not change anymore. So that's good, right? Just imagine I'm walking forward and I can be slowing down despite walking forward and then come to a stop. Yeah? Why there's, so there is no delta H. That makes it easier for current to flow because we still have the pump. So in that case, on the left side, and by left we mean the earlier time, to the left of the arrow, is it here? There we go. So for the early time, this diagram on the left is the same one we're talking about. There's no delta H, so that term cancels. There's no delta P, so that term cancels. So we're just left with 0 equals E pump over volume minus IR, or E pump over volume equals minus IR. So I is definitely not 0 there, right? Because this equation has to be satisfied. So there is flow because the pump is pushing the water. Delta H is going to prevent that, if anything. Yeah, so the pump is the key there. The reason I switched to this way of looking at it with the pump instead of just the two equalizing just because of gravity is because this is more comparable. It's like an easy analog, to circuits and how we're going to talk about non-steady state flow in circuits, but we'll get there in a sec. Okay, so that was a lot of talking, but the real takeaway was that we have some delta H, the difference in height between these two water columns, and the rate at which that delta H changes, how quickly delta H is growing, depends on the value of it. When H is small, it's growing quickly, and when H is large, it's growing slowly and eventually comes to a stop. And the final thing there, we can say the same thing about I. So, like we said before, there's this clean relationship between the current and the delta H. And so if H follows this behavior, I is going to as well. We'll see that more clearly in a sec, but it's also, we can kind of read it off of this plot right here. We know we have some current here, and it's going to be higher because it's easier for the pump to push the water when the water levels are equal, right? There's no potential energy difference to make it difficult, so the current is high. Remember, like very simple, just linear transport. The stronger the pump, the like larger the voltage difference, greater the pressure difference, whatever, the greater the flow. So in this case, we have a large pressure difference, or energy density difference because of the pump. It's unimpeded by any minus rho GH, and so we have a large I here, and then later on, our I is decreasing, but the rate of change of that I depends on its value. So I think I kind of lost myself in that line of thought. But if you can believe it for H, just extend it to I for now. So the way we describe these things, something where the rate of change of this thing depends on its value, is with an exponential decay. So this is just completely generalized. You've probably seen this equation in some math class. Here, I just say y of t. This y could be the height difference. It could be voltage. It could be later on charge. It could be pressure difference, anything. But it's some value that's a function of time is equal to some y naught, which is its initial value, and then times e to the negative t over tau, which is, we'll go through exactly how it works, but it's exponential decay. So what it's saying is we have something that's value we want to track over time. We have an initial value, and then as time moves on, this exponential decay will push that value down to 0. So we can see that by plugging it in, and I plotted it out here. So on the x-axis, we have time. So over here is our start. This is t equals 0, and as we move further along the axis to the right, this gets later and later in time. If we plug in 0, so times 0 for y, e to the 0, or e to the negative 0, whatever, e to the 0 is 1. So that's, you won't need to know much about like how to manipulate like exponentials and stuff, but the two things to know are that e to the 0 is 1, and e to the negative number is just 1 over e to that number. So e to the negative 1 is 1 over e. E to the negative 2 is 1 over e to the 2, or e squared. Those two things are important to know. But you'll do a lot of this math, like actual manipulation on FNTs and in DL. We're more going for just the behavior here. So anyway, we plug in t equals 0, and we just get out our initial value. Or on the graph here, at time 0, we have our initial value. It hasn't decayed at all yet. So in this case, this would be maybe our change in height or our current. Like our change in height hasn't started changing yet. Our current is at its maximum value. It hasn't started changing. But then, let's go forward in time. Let's plug in for some time tau. It's called the time constant. I'll go through a lot more what it means, but just mathematically, if we plug in t equals tau, which is just a constant in this equation, we get e to the negative tau over tau, which is 1. So we get e to the negative 1, or y of tau is y naught over e. E is like 2.7 or something, but it basically works out to a third of our initial value. So initially, we had our full initial value. After some amount of time that's related to this, whatever tau value is, we've decayed down to a third-ish of our initial value, or 1 over e of it. Then, if we plug in a really big number for t, so this is just saying t is much bigger than whatever this number tau is, a huge number, then we have y naught times e to the negative huge number, which would be 1 over e to the huge number, which is tiny. It's essentially 0. So if we plug in a really big value for time here, we get 0, which, same thing on our plot, if we go really far out in time, our initial value will have decayed down to a really small value. This isn't, like it doesn't, mathematically this will never actually be 0. It's like asymptotic, so it never crosses the x-axis, but physically that's just kind of an artifact of our model. In reality, if I have a certain number of water molecules on this side that are flowing onto the other side, at some point the last one is going to do that, or it's going to stop. So this will like in physical systems, they do come to a rest. But for our purposes, it's just, it asymptotically gets there. It's close enough. Okay, so to sum up, the reason we wanted this is because the rate of change of y depends on the value of y. Does that happen here? Well, what about this graph tells us the rate of change of y? When you think rate of change, what can we also call that? Slope, exactly. So let's see what the slope is at different points in this graph. Does it change? Well, early on, we have a pretty steep downward slope, right? And then as we move on, our slope gets less and less steep in time. If we go really far out in time, it's essentially flat. Our slope is 0. So that makes sense. Over time, y is changing. The value of y is decreasing. And as a result, the rate of change of y is decreasing too, which is exactly why we wanted to use this exponential, because we have this relationship that the rate of change of y decays over time to 0. Not just y decays to 0, but also its slope. Okay, so I know that was a lot to process right here. Let's talk about the time constant. So I just said use it as some reference. And mathematically we know that this time constant tells us when the thing has decayed to about a third of its original value. But what else does it denote? Well, in general, it's just like the time scale that our system evolves on, right? So if our time constant is a few seconds, we know that our system will go from start to equilibrium in a few times that, like a bunch of seconds. If our time constant is 3, by 20 seconds, we're going to be completely in equilibrium. If our time constant is an hour, then we'll have to wait till, a bunch of hours, 5, 10, whatever, but a good bit more than that time constant in order for it to come to equilibrium. So it just kind of sets that time scale. If we have a big time constant, that's a slow-moving system. It decays very slowly over roughly the scale of that time constant. If we have a time constant that's milliseconds, our system's going to go from initial to equilibrium super quickly. Its value depends on exactly what system we're referring to. For fluids, it depends on resistance of the pipe, it depends on the density of the water, the area, all these different things. You'll work on that a little bit in DL, but you won't have to prove any of that. But we do just want to know that it's related to, the setup of our system determines how long it takes to evolve, right? And I think that makes sense. A system with a ton of water in it is probably going to evolve slower than just a little one, right? So that's basically what we're going for with that. And it gives us this characteristic time scale. The other thing it tells us, in addition to telling us that the value of y decays to about a third, or 1 over e, in one time constant's time. So by time t equals tau, we're down to a third. It also denotes like two regions. Earlier on, like t is less than tau, we get a steep slope, right? So this is where it's very rapidly decaying. We started at y naught, and then we're dropping down really quickly. But then after t equals tau, so t is larger than this tau, the slope starts to mellow out more, and it decays a lot slower. So in addition to giving us how much y has decayed by, it's also giving us an idea of how long the rate of change takes to develop. And just putting that more explicitly, when t is less than tau, this should tell us that the units of tau are time, right? Is our time constant, characteristic time. When t is less, we get large or like undecayed values and steep slope, quick change. And when t is greater than tau, later times, we get a value that is significantly decayed and is evolving more slowly. So let's try to just relate this to the system we were just talking about. So I have this system where we have two fluid columns, initially at the same height, and I put a pump in between, which is going to force water from the left to the right. And over time, we know, again, the height differential, the delta H, changes, grows, and in addition to the delta H growing, the rate at which it's growing decreases until it reaches a stop. And in our final time, I is about 0, and the delta H reaches some maximum. So let's try to identify the equivalent, where each of these snapshots falls in to this graph of current over time. So we know this, we haven't proved it mathematically really, but we know this vaguely fits the evolution of this system for current. In this initial state, like we said, it's very easy for the pump to push water from one side to the other because there's no delta PE over volume, which is why we have a very large initial current. But then over time, it gets more and more difficult, so our current decreases until it reaches 0. So the plot makes sense with the story, and we can kind of put these on there. Initially, we have our undecayed initial value. That lines up with A. When we first connect it, delta H is 0, and I is its maximum I naught. Then, after some amount of time, the system has partly evolved. It's still evolving. H is still growing, but it's slowed down. The slope is less steep, and H has decayed, and so has I. The flow rate has decreased. And then finally, somewhere along here, in this case, I implied that I equals 0, but it should be somewhere out here. After a long time, delta H is big, I has decayed down to 0, and the rate of change of H and I have also gotten really small. So the graph does kind of tell the story of what we're looking for here. And this tau, this value that's characteristic of the system, gives us an idea of how long it takes us to get from A to C. Not so specifically A to C, but how long it takes to get from I naught to that decaying to I naught over E, which, it's the time scale. You can use that to figure out, okay, well, if I know this is how long it takes to get to I naught over E, how long does it take to get to I naught over 2 or I naught over 10, something like that. You'll work out that type of math, talk about something called the half-life, which is very closely related to this. You'll do all that in DL and on FNTs. So now let's talk about the height difference. Let's make one of these plots for the height difference. Like I said before, it also follows some sort of exponential decay, right? We have some value of H that's slowing down over time. The rate of change of H is decaying, but H doesn't decrease, right? We know this, and I switched to saying H here. I mean the difference in heights. So I mean the change in height from the top of this column to the top of this column. On the next slide, I'm just going to call it H, but I do mean the difference in height between these two. And that value is growing, right? So this graph does not, we can't just take this exact thing, relabel it with H's, and call it a day, because this would tell us that H starts at some value and shrinks. And we know that's clearly not the case. The thing we do want to preserve is the fact that the slope is decreasing over time, right? We want it to get less and less steep. So like we said, we know the rate of change of H depends on the value of H. So we know we want an exponential. And we know that this function will not work. If I just swapped out the I that I had before for an H, it doesn't work because that tells us H decreases, which isn't the case. So how do we make up for it? I'm just going to give you the answer. You'll never have to derive this. But again, we'll do the same thing as before. We'll just take it and make sure it works. So same setup before, A, B, and C moves forward in time from the initial, where it's very high current, delta H equals 0, to the final, where there's some maximum delta H and I equals 0. And we'd want the change to slow down over time, even though H is growing. So let's see if this graph shows that. Well, at time t equals 0, at the far left-hand side of this graph, our H is 0, which is good, right? In our initial, in point A, we have no height difference. Perfect. And then, as we move to B, we develop some height difference, which is what this graph shows. And then, even more, as we go to C, we get an even greater height difference, and it does slow down over time, right? The slope is the steepest here, and as we move forward in time, the slope gets shallower and shallower, less steep, until eventually it reaches an asymptote at its highest value of h, so h naught. We still call it h naught, but at this point it's its maximum value instead of its initial. The equation up here is very similar to the one we showed before, except instead of h times e to the negative t over tau, we have h times 1 minus e to the negative t over tau. And we can plug in some values there to make sure it works. Time equals 0. We'd have 1 minus e to the 0, which is 1 minus 1, or 0. That's how we get this. If we plug in a huge value, we get 1 minus e to the negative huge value, which is essentially 1 minus 0. So we get h naught after a lot of time, which is perfect, right? We want to start at 0 and evolve asymptotically toward h naught with a decreasing slope. So it works out. So this is exponential decay. The key takeaway, I think, you'll see all the curves that you draw and analyze for exponential decay, non-steady state, which is a form of non-steady state flow, will either look like this or like this. I mean, you'll have different scales, right? Like the markings on the axes will be different, but it'll either be this concave up curve like that or concave down kind of like this. The similarity is that the rate of change is decaying, right? The slope is decreasing. The value of whatever we're plotting does not decrease. In this case, h is increasing. On the other slide, we saw that I is decreasing. So decay does not refer to h or I. It refers to the rate of change of h, the rate of change of I. That's what we mean by decay. It's a decay in the flow rate or the evolution rate of the system. All right, questions on the, any questions about the math of how an exponential works? Again, there's a lot of stuff here. Plugging it in a few times really helps. And remember, tau is this time constant. Larger tau, slower evolving system. Smaller tau means it evolves quickly. And I've plotted tau on here too to just show us, in this point, since h is growing, instead of tau being the point at which h is about 1/3 of its original value, since we're growing toward its maximum, instead it will give us when h is about 2/3 of its final value, or 1/3 away from its resting. There's only so much we can do here without working through some math together. So let's transition to electrical circuits. Why did I pick this system, which is a little more convoluted, instead of just having one cylinder with a higher water level flow into the other? Why did I have a pump push them to be separate, or to have a delta H? The reason being is that is very comparable to the way a capacitor works. A capacitor is our new circuit component. Before we just had batteries and resistors, now we're adding in a capacitor as well. And these act as a reservoir for charge in a way. So what does that mean? Well, let's start with a battery hooked up to two neutral plates. And by neutral, I mean it has an equal amount of positive and negative charge. The net charge on either plate, add up all the protons, add up all the electrons, and you get 0. So there's no preferred charge on either plate. But since the battery is there, we know that a battery sets up a voltage difference, right? On the low side of the battery, we have a lower voltage. And on the higher side of the battery, we have a higher voltage. And so that's like, in this case, when there's no delta H, that's like the plates being neutral, having no net charge. But when I put the pump there, it creates this energy density difference, and that's why one rises higher than the other. Same thing with the battery. The battery is our pump now, and that's going to pump charge from one side to the other until we reach something like this bottom picture here, where on the right side we have an excess of negative charge, so the total charge is less than 0. And on the left-hand side, we have a total charge that is greater than 0. So it created this charge differential, and it's eventually going to come to a stop, right? The battery is only so strong. It only has so much, it only has a certain voltage. And so assuming there's some thing that's keeping us from adding more charge here, Like in this case, we had the potential energy difference. That's canceling out the pump. And so once the potential energy difference rises high enough to completely cancel the pump, there's no more flow. Same thing happens for the capacitor. As more and more charge flows to this side, it gets more and more difficult to put that charge there. And eventually, it's so difficult that the battery can't add any more, and so the current stops. And now we have these two charged plates. Very much like in this case, the pump stops and we have these two water levels that are different. So why does this occur? What's keeping the battery from pushing more and more charge from one side to the other? Why does it get difficult? Well, this is kind of just summing up what I just said before. I'll go back to this. So why is it difficult? Let's say we start with a neutral plate. So like this is the one that has an equal amount of positive and negative charges, right? And so there's no net charge. And then I put one positive charge on there. That's fine, right? Just put it on there. It's neutral. It's easy. Flows on there. But now I put another one on. Now I put another one on. They repel. Two positive charges don't want to be near each other. They push apart. Same thing with two negative charges. Any two like charges repel, just like opposite charges attract. But the more and more of these like charges I put on the same plate, the more and more they push apart, and it gets crowded. I only have a finite amount of space on each plate, and so as I pump more and more charges on there, they're pushing apart, they're running out of space, and it becomes difficult to add more. They don't want to be there anymore. So that's why as the battery charges one plate, adds a lot of positive charge to one side, creates a lot of negative charge on the other, at a certain point it's so difficult to add another one. They're all repelling each other strongly enough that the battery can no longer do any more. And as that happens, we know that our current is going to decrease. Just like in the water level scenario, the current decreases when it gets really tough to pump more water. Right? It's difficult, so the flow rate decreases. The battery can't push water as quickly. In this case, the current, the rate of change of the charge decreases as well because it becomes more and more difficult for the battery to create that charge differential, so our current goes down. So now going back to this slide, we know it works with our exponential decay model, right? Because the battery drives charge from one side to the other. We have some initial flow rate and some initial difference in charge. And then over time, those two things change. The flow rate starts with some value and then decays to zero as it gets more and more difficult to add charge. And then the charge part acts like the height, where the charge is growing, but the rate at which the charge is growing slows down. So we get a very similar relationship that we did to the fluid flow one, where the rate of change of both the charge difference and the current are decreasing, even though the current is decreasing and the charge difference is increasing. Okay. The battery is driving that change. Great. So it is exponential decay. So now let's try to describe that like using equations. How do we describe this rigorously? Well, there's something called the capacitance. That's it's kind of the analog of the physical properties of the cylinders that have the water in them. The capacitance determines how much charge I can put on a plate with a given amount of voltage. So if I have a larger capacitance, I can put more charge on that plate with the same amount of voltage. And it's related to the physical properties of what that plate is. Remember we said the reason it gets difficult to put charge onto a plate is because there's a finite amount of space, right? As I put more and more charges, it gets crowded. So one way I can increase the capacitance is if I increase the size of the plates, right? If I double the space, I double the amount of charge I can put on there, and so my capacitance will go up. And that gives us these relationships here. I mean, these are the same in this red box. These are the same equations. I just rearranged them. But if we look at the expression on the left here, the amount of charge that's built up on either of the plates is equal to the capacitance times the voltage difference between the two set up by the battery. So if we either increase the delta V, so put a stronger battery there, that will increase the amount of charge, right? A stronger battery can pump more charge, resist more of that repulsion. Or I could increase C, increase the capacitance. I could keep the same battery, but if I make it easier to put charge on those plates, the amount of charge on them will also increase. And you can rearrange that to solve for the change in voltage. If I know the amount of charge on the capacitor, and I know its capacitance, then I can figure out what the voltage change in between the two plates is. Okay, so let's put it in a circuit. Seems like a big jump, but all I did was take this previous setup and bend the two plates together. This is still technically a capacitor the way I've drawn it, but if I just take those two plates and then bring them closer together so they look more like they fit in a circuit, right? Now they're close together and we have something that looks more like a circuit or a loop. But notice there still is a break in between the capacitor. Like when we were doing circuits with just batteries and resistors, if there was a break in the wire, like an open switch or something, that means the current's zero, right? No charge can flow across this. But the key with the capacitor is that since we have these neutral plates, we have somewhere where we can pull charge from and deposit it. So the way it's set up here, and remember the current is the flow of positive charge, so when I say moving charges, physically what's happening is electrons are being removed from this side, which makes this side positive, and they're being deposited on this side, which makes this side negative. But the way we describe it, for whatever reason, is that we're removing positive charges from this side and depositing them here. Either way, we get a charge differential where one side becomes net positive and the other side becomes net negative. So because these are these neutral plates, they're like reservoirs, we can still have current, right? The current doesn't flow all the way around and jump across, but it does get pulled from one side and put on the other. But what that implies is that it will come to a stop, right? They're not infinite, we can't just keep pulling charges all day long. Remember we said it becomes difficult because these like charges don't like to be near each other. So at a certain point, that's going to come to a stop, and the capacitor will be full. A circuit with just a battery and a resistor, well, assuming the battery doesn't run out, will just run forever, but we put a time limit or give a time scale to this circuit by how much charge we can pull from one side of the capacitor and deposit it on the other. So we can use it in our loop rule very similarly to the way we would have a resistor. Starting just before the battery, same thing as before, we have an E or an epsilon from the battery, so it's a voltage gain. And then as we go around the circuit, let's look at the IR term is easy, right? We have current flowing around, so we still get the same minus IR. And for the capacitor, now we have this other term, this minus Q over C, which is just our delta V Q, or delta VC, whatever. It's the voltage difference across the capacitor. And the reason it's negative is because we know current is flowing clockwise here. And clockwise, we go from positive to negative charge. So when we're going through our loop rule, when we go through the battery, we know current flows from negative to positive. So when we jump through the battery, we get a plus, a voltage increase. Here, it's just doing the opposite. We're going from plus to minus, so we get a decrease. So it acts just like a resistor, and that's a gross oversimplification. But in the loop rule, it looks kind of like a resistor in that you just pop in whatever voltage change occurs across the capacitor. That's the way the loop rule works. We have it's a sum of voltage changes in a loop, and those all have to add to zero. So a battery's voltage change is plus epsilon, a resistor's voltage change is minus IR, a capacitor's voltage change is minus Q over C when it's set up like this. So let's trace that over time. Like we said, the current is going to change over time. So time zero. This is when we first connect this circuit. The capacitor is still neutral at this point. Charge has not flowed from one side to the other yet. So what would our voltage drop be across the capacitor? Well, kind of make it clear, it's zero. Remember, this is equal to Q over C, the charge over the capacitance. So if no charge is built up on here yet, Q over C is just zero, or our delta V is zero. Another way to see it, the reason we had a voltage change is because we went from plus to minus, but now these are just both the same. So there's no voltage change, and our loop rule looks just like the capacitor wasn't there at all, because before there's any excess charge, it's very easy. Like the battery sees no fight from these charges to pull a charge from this side and put it on that side. And this will be what our maximum current is. When we first close the loop, it's as easy as possible as it could be for the battery, and so at time 0 we have the highest current, just like we did for the fluid circuit. Now let's evolve a little bit, not all the way to equilibrium, but we build up a small amount of charge on the capacitor. Now it's getting more difficult to keep moving, right? Because now these negative charges don't want another negative charge here. These positive charges do not want another positive charge there. So the battery, it's harder and harder for the battery to keep moving. This means our current is going to go down. Also in our loop rule, we do have this minus Q over C, because we do have some jump from positive to negative in the circuit. And if we solve this out, this shows us that our I does have to decrease. This if we just move the minus IR over here, we would see that without this term, IR is just equal to epsilon. Great. But once we add this in, IR is equal to epsilon minus Q over C, minus the voltage drop here. So there's less current going through the resistor after some time. Then let's take it all the way to equilibrium, so way longer than whatever the tau is for this circuit, the time constant, like the characteristic time. Now the battery can no longer push any more charge from this side to that side. It's too difficult, and so our current goes to 0. That means our loop rule loses the minus IR term, right? Because if I is 0, minus IR is 0. So the only things we have are the voltage change, the voltage increase from the battery, and the voltage decrease across the resistor. In other words, the resistor just has an equal and opposite voltage change as the battery, right? There's no more flow. I is 0 in this circuit, and this almost works. This acts like when we're just at equilibrium, almost like we just had another battery with an equal voltage just flipped around, right? We built up this potential difference to oppose it. They're perfectly in equilibrium, just like the pump was perfectly in equilibrium with the delta H. Now the epsilon is perfectly in equilibrium with the Q over C, and we're in steady state. Or not, it is steady state, but really it's equilibrium. There's nothing moving at all. So let's put this on our exponential decay curve, or try to match this up with the function we had before. Just like our height was increasing, but the rate of change was decreasing, our Q, our charge on the plates, is increasing, right? We're building up a net charge on either of the plates, but the rate of change of that buildup is decreasing because it gets more and more difficult as there's more and more charge on it. So yeah, the shape does work pretty well. Same type of things happen. If we plug in t equals 0, we get Q equals 0. We plug in t is huge. We get Q is this Q naught, its final value. And there's this time constant that tells us this characteristic time scale for how quickly this happens. You'll see this in DL2, but the time constant is related to, really the only two things that it can be, the resistance and the capacitance, so just like the physical properties of the circuit. And if we want to match up these moments in time, these snapshots on the left with points on the curve, we can see that early time, no charge on the capacitor. We have a very small charge or 0 charge, but it's very quickly changing. The charge is building up quickly because it's easy to do. Then it starts to slow down as some charge builds up. And then once all of the charge has built up, it's no longer changing. So just like we wanted for exponential decay, Q increases, but the rate of change of Q, which is really the thing we're looking at for decay, the rate of change of Q is decreasing over time, decaying to 0. So that's our exponential decay for the capacitor. For current, it's the opposite, the opposite from charge, but the same thing that we had for the fluid circuit. Current starts off high because it's easy to push charge around the circuit, and then it decays to 0. And the rate of change decays to 0 because it becomes more and more difficult to push current around. So we get the same setup. Then finally, this is just a little extension of this, you can discharge the capacitor too. Let's say after I charge it up, I take out the battery. Now there's nothing to counteract the resistor. So my loop rule is only the capacitor term and the resistor term. And it turns out in this case, just like in that quiz practice example where you have two batteries facing opposite each other, the stronger one wins. In this case, there's nothing opposing the capacitor. There's nothing setting up a voltage difference that's opposite it, like the battery. So instead, the current actually flows in the way that the capacitor wants. These positive charges want to get out of there because they're packed in here, and so they flow, in this case, counterclockwise and discharge. Now, over time, each positive charge is going to flow around, cancel out one of these, and we'll end up with a capacitor that is completely discharged. So when I hook up a capacitor over a battery, it charges up over time until it can't anymore and it's at its maximum charge. And then if I remove the battery and connect it just across a resistor, it will discharge. And it turns out the qualities of that discharge, like over time, are also exponential. Because at first, it's really easy for the charge to flow around, and then the thing that's actually driving the flow, this change in voltage, decreases. Like once there's only one charge here left and one charge here left, that delta V is very small. And like we saw before, when this delta, our gradient, is really small, our flow also decreases. So you'll see a lot more of this in DL, but this is just a preview of it. And that's all I got. Have a good rest of your week.